Alright guys, today we're going to talk about empirical and molecular formula. So let's go ahead and get started. Now, the molecular formula of a compound represents the arrangement of atoms in a whole number ratio distribution. The empirical formula is very similar to that. However, there's a caveat that the empirical represents the simplest whole number ratio of atoms to make a compound. So, when you compare them, the molecular formula can sometimes be the empirical formula. And sometimes an empirical formula can be different molecular formulas. And we'll see some examples. Let's look first at, notably, this H2O. Now, H2O is water. The molecular formula of water is H2O. However, the empirical formula is also H2O. It represents the simplest whole number ratio distribution where there's going to be one hydrogen, there's two hydrogens and there's one oxygen. That's the smallest those numbers can be simplified to as a ratio. Now, if you look at the comparison between this compound and this compound, the molecular formula of N2O4 is represented here to the right. Now, this is not the simplest whole number distribution of those atoms. And so if you were looking for the empirical formula of that compound, it would be NO2, where instead of having two, you now have one nitrogen, and instead of having four oxygens, you now have two oxygens. And if you're comparing these, once you see that these are basically different by a factor of 2. So if you essentially divided this by 2 and this by 2, this is what you'd end up with for the empirical formula. And as you can see, it can be simplified no further than that as far as whole numbers are concerned. And so that's characteristic of empirical formulas. Now, if we look at this same example here, we have N4 and O6. Those simplify to N2, O3 respectively. Now, let's look at how they compare. Here you have 4, and if you divided that by 2, you'd end up yielding 2. If you divided this by 2, you would yield 3. So here again, you're finding the simplest whole number. This cannot be simplified any further. If you did try to divide this by 2, that would end up being 1, and this would be 1.5. And that's a fraction. You can't have a decimal point ratio for your empirical formula or your molecular formula. They need to be whole numbers. And so let's look at this last one, because it's going to add a dimension to what we're going to be using empirical formula for, and that's kind of to determine the difference between the molecular formulas of different compounds. Here you see the molecular formula of C2H4O2 and C6H12 and O6. Now, between the two of them, they both yield the same empirical formula. If you divide this guy by 2, you end up with C1, H2, and O1. Conversely, if you look at this distribution of C6, H12, and O6, the empirical formula is the same, and you achieve that by dividing by a factor of 6. So comparatively, you can see that these guys have the same empirical formula, however they have different molecular compound formulas. Now, what's going to be useful for this as a concept to know is that there will be questions where you're given information about the empirical formula of a compound, and you're tasked with determining the molecular formula of that compound. And the discernible characteristic lies in not only the number of atoms, but their respective atomic weight. And so if you were using the atomic weight and comparing the empirical formula, both of these yield the same empirical formula. However, their distribution of weight is definitely different, and that will be one of those discernible characteristics when you're tasked with asking questions about that you use to kind of find out the answer. And so let's go ahead and look at how one would go about solving empirical formula-based questions first. Now, I took a minute to go ahead and jot down a few kind of notes about empirical formula when I'm solving. Now, for me, when I'm given a percentage for an empirical formula question, I usually assume that I have 100 grams of substance. You don't have to always assume that. Sometimes the grams are actually given to begin with, and all you have to do is proceed to step 2. Now, for step 2, I invite you to divide by the element's molar mass. That can be found on a periodic table of any of your compounds. You're going to divide the individual atoms by their characteristic mass, and that's going to give you kind of a distribution of mole if you want, or in some cases a mole fraction, depending on what you're starting with. After that, you're going to divide each of those by the lowest mole value of those. So we'll see an example where that gives more of a practical scenario. And then lastly, that should give you a distribution of whole numbers, but if it doesn't, you're going to kind of apply a multiple or something to devise the appropriate mole ratio, or not really a ratio, the subscript number of those number atoms. And so let's go ahead and take a shot at some of those questions. We're going to look at our first example here. Now, in this first example, we're going to pay attention to the percentages given. Here we're given a percentage of 68.4 chromium and 31.6% oxygen. Now, in a perfect scenario, these percentages add up collectively to 100%. Knowing that, I can go ahead and assign these guys as saying it's equal to 100 gram. And in this case, I'm going to assume that instead of having 68.4% of chromium, I got 68.4 grams of chromium. And I'm going to assume that I have 31.6 grams of oxygen. Now, the next step I'm going to use as my step 2 and my little kind of devised generic instruction, and that's where I divide the mass by the characteristic molar mass. And so to do that, I look up the molar mass of chromium and I look up the molar mass of oxygen. Now, you're going to use the molar mass of oxygen atom, not the molar mass of O2 atom. It's not diatomic in this case, so you want to make sure that you're mindful of that. Chromium is 50, I don't know, let's say 52, because it's like 51.99 or something like that. So I'm going to assume 52.0 grams. And then my oxygen is actually going to be 16, as I mentioned earlier. And that's going to represent the first step that I use when solving this question. So I take my 68.4 grams and divide that by 52 because that represents the chromium. And that's going to yield 1.3, well, let's say 32, roughly. And then I take my 31.6 and divide that by 16. And that gives me roughly 1.975. Now, I then proceed to divide by the smallest of these two. The smallest is going to be this guy, 1.32. So I'm going to divide each of these by 1.32, divide this by 1.32. Any number of times self is an identity function, that's going to yield 1. But 1.975 divided by 1.32 is going to give me a number that's 1.4, which I probably rounded approximately to 1.5. Now notice I said 1.5. I'm not going to round that 1.49 number to 2 because that's not what you're supposed to do. Remember, we're trying to achieve a whole number ratio, and if you round prematurely, you end up getting the wrong characteristic empirical formula. So, next, because I know that chromium cannot be represented as Cr1 oxygen 1.5, I need to find a whole number ratio that's close to these. What I'm going to next do is multiply these by 2 because that's going to be able to put those numbers in kind of a number or round them to give them a number that can be more closely associated with a whole number. And so 1 times 2 obviously going to be 2. 1.5 times 2 is going to yield 3. And so my representative empirical formula would be chromium 2, oxygen 3. Now, we don't know anything about the molecular formula. We know the empirical formula is Cr2O3 of that compound. And so technically this compound, if it was molecular formula, could be much larger, or it could be that same very compound. But we did find the answer. It is Cr2O3. Okay? So that's how you solve a question where you're given kind of a percentage, and then your goal is just to assume that you have 100 grams of substance and proceed with solving that question. And so we're going to go ahead and take a look at another example where we're kind of challenged a little bit more. And in this question, we're actually going to look at how this breaks down when you have masses. So we're looking at question number 1 here. Now, question number 1 is unique to the previous example in that you're given actual masses of the representative compounds to begin with, whereas before we were given percentages and we just assumed that they had a certain gram breakdown. Now, if you add these masses up, it ends up being roughly 1.5 grams. But you don't need to know that. What you do need is to kind of apply the same steps that we mentioned, where you're going to apply step 2. So you're going to take your 0.783 grams of carbon. You're going to take your 0.196 grams of hydrogen, and you're going to take your 0.521 grams of oxygen. I hope I said it in the right order. Now, and then you're going to divide them by each respective molar mass. Molar mass of the monatomic species, not the diatomic. So, for carbon, it will be 12.01. For hydrogen, 1.01. And for oxygen, it will be 16. Alright, so using my trusty calculator, we then input our information. 0.783 is divided by 12. That yields roughly 0.065, and we'll say 3. And that's the carbon. Next, we have our 0.196, that is divided by 1.01. That yields 0.194 for the hydrogen. And lastly, but certainly not least, 0.521 is divided by 16, and that yields 0.032, and we'll round that to 6 for oxygen. Now, what we're going to look at is which one of these is the lowest number. Now, the lowest of these is going to be this guy. And so we're going to divide all 3 of them by that number. Here we got identity function again. That's not that's oxygen, sorry. Divide that by 0.0326. And divide this one by 0.0326. So here we got 1. We're going to move to this next one, 0.194 divided by 0.0326 yields roughly 5.95. And then this one here is 0.0653. And we're going to divide that by 0.0326, which ends up being somewhere close to 2. All right, and so for these guys, these numbers are so close. This number is like 5.95, but roughly speaking, you can approximate that value to 6. Now, the reason I would encourage you to approximate it to 6 is that the number falls above kind of 5.91. It falls above that. So if it was below that number, like it was like 5.8 or 5.85, I perhaps would imagine that we would need to multiply it by some number to get a whole number ratio distribution, whole number subscript distribution. But in this case, I'm okay with rounding this number to a whole number. So this ends up being rounded to C2. This hydrogen gets rounded to 6. And then this oxygen gets rounded to 1. And this represents the empirical formula of that compound. Notice the difference between this and the first question is that in the first question, we were given a percentage. We assumed them to have a certain characteristic mass and then divided by the molar mass and followed the same steps. Here, we took the mass given, divided by their molar mass, and then followed the same steps of dividing by the smallest and then appropriating a ratio or subscript distribution, whole number wise. So, that defines the process used for determining empirical formula, both using a percentage where you assume it to be a certain mass or when you're given a specific mass. We're now going to explore a heightened depth of questioning that aligns with determining the molecular formula of compound. And with questions of that caliber, you want to kind of have an idea of how they relate to each other. You need to understand that empirical formula is the simplest whole number ratio of a molecular formula. And sometimes the molecular formula and the empirical formula can be one and the same. So let's go ahead and look at this question here where we have an example. They've given us the empirical formula in this question. They've given us a molar mass, and they want us to find the molecular formula of that compound. Now, we can use the empirical formula and compare that to the molecular formula of any compound, because the empirical formula represents kind of the simplest ratio of those subscripts. And so whatever CH2 empirical formula is, it can be any number of molecular formulas as we've seen before. It can be C2H4O2. It could be C3H6O3. It could even be C4H8O4, and so on and so on. Now, what differentiates these guys is the fact that they have a different distribution of atoms, and they're going to have a different characteristic molar mass. And we're going to use that molar mass to our advantage. Now, the first step I would invite you to do is to determine the molar mass of the empirical formula. So, the empirical formula for CH2O is going to be 1 carbon, where you have 1 times 12.01. You have 2 hydrogens times 1.01. And then you have 1 oxygen, which is 16. And I multiply, that ends up being 12.01, 2.02, and ends up being 16. Now, if I added those guys up, I'd end up with something like 30.03. And that's the mass of CH2O. Now, my molecular formula has some compound that has 180 grams. So we don't know what that compound is. But we know that there's a kind of a 1-to-1 ratio, if you will, of distribution. So what I would invite you to do is take the 180, divide that by the molar mass of the empirical formula, which you can say 30.3, and that roughly ends up being close to 6. Now, knowing that's a 6, I'm going to multiply my empirical formula subscripts by 6 for each atom. So for C1 times 6, that's going to be C6. For H2 times 6, that's going to be H12. And then O1 times 6 is going to yield O6. And so my molecular formula is going to be C6, H12, and O6. And so if you fact check the actual molecular mass of that compound, you'll find that that has a very close approximation molar mass that's closer to any of the other ones would have that would have an empirical formula, CH2 oxygen. Now, for a similar question, if you're given the mass, you're going to kind of use the same steps. Meaning, if you're given a question like this guy, you're going to use the same steps where you find out your distribution and kind of go from there. But the process is not any different. For this question, the only difference is you'd first be tasked with determining the empirical formula and using that to extrapolate the molecular formula. And so use all of the steps that were used in this question, and then from there, once you find your empirical formula, use that to find that answer, which you have 62 grams. And so that completes our lesson on empirical formula and determining molecular formula of compounds.